Hello everyone, my name is Georgios Kouros from the PSI lab of KU Leuven, and I'm going to present you our joint work with Fort Greenfield Labs on pose estimation titled Category Level Pose Retrieval with Contrastive Features Learned with Occlusion Augmentation. The main focus of our work involves doing pose estimation at the category level, which means we want our model to generalize to entire categories of objects, such as cars, which may vary considerably. To do that, we use contrastive learning to learn how to extract highly discriminative features, which we use for pose retrieval. In order to be able to handle really complex scenes with foreground occlusions, background clutter, or a lot of appearance variations, we use strong data augmentations. Our pose estimation architecture is composed of two pre-trained ResNet 50 encoders, EC and ER, that are fine-tuned in a multimodal contrastive learning setting for comparing real objects with renderings with respect to their pose. The comparison is done in an embedded feature space that allows for focusing on pose-relevant features and ignoring irrelevant appearance information. In order to achieve real-time inference, we generate a database of renderings and encode them offline, and then simply do nearest neighbor pose retrieval. We jointly fine-tune the ResNet 50 encoders EC and ER with a contrastive loss, but we avoid the discretization of pose labels to bins by incorporating the geodesic distance delta theta into the loss function. This makes the distance between two samples in the embedding space proportional to their actual geodesic distance. The use of such a continuous pose label space improves both the accuracy and generalization of our model. We also help the model learn faster and more efficiently by doing pose-aware sampling and mining of positive and negative sample pairs by thresholding on delta theta rather than binning. To improve the performance of our model, we use an elaborate data augmentation scheme that includes augmentations such as horizontal flipping, random Gaussian blurring, color jittering, bounding box augmentation, and synthetic occlusion augmentation. In the bounding box augmentation, the corners of the bounding box are augmented by at most n pixels horizontally and vertically, where n is a function of the lower boundary on IOU. In the synthetic occlusion augmentation, each input image is artificially occluded by 1 up to 8 occluders, which are rescaled and translated before being pasted on top of the image. The rescale factor of each occluder is calculated as the product of the occlusion scale S, which is a hyperparameter, and X, which is a random number sampled uniformly between 0 and 1. Moving on to the results, we trained our model on the training set of Pascal 3D and evaluated it on the test set of Pascal 3D and its artificially occluded variant occlude Pascal 3D, where L0 corresponds to Pascal 3D and L1, L2, L3 correspond to occluded variants with increasing levels of occlusion. We used three metrics for the evaluation, namely the accuracy with a threshold of 30 degrees, the accuracy with a threshold of 10 degrees, and the median error. And we outperformed the competing methods in the vast majority of metrics and occlusion levels. We also evaluated our method on Kitty 3D without retraining, and we still outperformed the strongest competing methods by a large margin. And we also know that when using strong bounding box augmentations during training, we achieve an even better cross-data performance. When observing successful retrievals, we see that the model learns to focus on category-specific information and ignore instance-specific details, thanks to training with multiple CAD models instead of just one for a specific category. When observing the failed retrievals instead, we see that most failures occur due to confusion about direction, same category occlusions, rarely seen poses, or atypical vehicles that were probably not seen during training. During the initial stages of our work, we experimented with different rendering types, such as RGB renderings, silhouettes, depth maps, normal maps, and triplet maps, which are basically concatenations of RGB renderings, depth maps, and normal maps. And when we compared them, we found out that normal maps perform slightly better than the rest of the rendering types. So that's the rendering type that we eventually used throughout our evaluation. However, we also know that our method works sufficiently well with all rendering types. In order to evaluate the effect of synthetic occlusion augmentation, we trained 5 different models, and we observed that the higher the occlusion scale during training, the lower the performance drop across increasing levels of occlusion during evaluation. To further evaluate the effect of bounding box augmentation in our model, we trained again 5 different models, and we observed that the higher the bounding box augmentation during training, the lowest the performance drop across increasing levels of test time bounding box augmentation. Finally, we conducted an ablation study to showcase the importance of the different parts of our approach. So first, we showed the performance of the complete model. Then we trained with only a single CAD model per category, so uh, not multiple CAD models. Then we removed the documentations in the form of Gaussian blurring, horizontal flipping, and color jittering. Then we added same category occlusion. So for the car category in particular, we trained with car occlusions as well. After that, we trained with discretized pose labels. Then we trained with triplet loss instead of a contrastive loss. And after that, we completely removed the synthetic occlusions. And finally, we trained without the dynamic margin, so a static margin that's not proportional to the geodesic distance of a pair of samples. And in all cases, we see that there is a non-negligible drop in performance, which showcases the importance of our design decisions. In conclusion, we propose a simple and easily reproducible architecture for category level pose estimation. We show that our approach achieves state-of-the-art results on Pascal 3D and Occlude Pascal 3D, and at the same time, we outperform the strongest competing methods on Kitty 3D. We also show that a simple architecture like ours with strong data augmentations can outperform a more complex and specialized architecture that's specifically designed for robustness to occlusions and background clutter like NEMO. And finally, we show that a simple pose retrieval scheme can be a fast alternative to slow and inefficient render and compare methods like NEMO without an impact on accuracy. Thank you everyone for your attention. You can find our code and train models at the following link and also on the shown QR codes.